for LeetCode today. That is problem number 877 called Stone Game. I will be describing the problem, then we will be reviewing the various approaches to solve the problem, and at last we will code the problem and discuss the time complexity and other details. So problem, then approaches, then solution. This acronym based uh, steps we will be following. Okay, so let me describe the problem first. The problem is such that there are two persons, Alice and Bob, and we are given even number of even number of piles of stones. Stones such as values could be 3, 2, 4, 1, 10, 7, 8, maybe. Uh, and again, it can be 2. So there can be any number of stones in a pile. That doesn't matter. That can be even, that can be odd, but uh, the total number of piles will always be even given, so that starting player doesn't have advantage over the other player, and uh, the sum of these piles of stones will always be even, always be, sorry, odd, so that eventually distribution, uh, so that we will have a deterministic winner. Winner is always decided. Okay. Now, how do we come to the approach section? How do we approach this problem? We see that uh, whenever a player uh, given the size of the pile, because pile is always being consumed either from starting or from the rear end, and so this is decreasing the size of my piles of stones to uh, by one at every turn. So that eventually uh, no stone pile is left in my sequence. So yeah, so after every iteration, the size is decreased by one. That is happening here. But it is for sure that piles are always that the stones are always consumed either from starting or from the rear end. So at for a given size of the array, we do have one choice, that either we start from either we pick the first the starting stone or pick from the ending stone, right? But the condition is that we have to pick in a such a way that we do have advantage over B, over the other player, basically. And how do we ensure that we we can't go greedy, because there can be a chance that you greedily pick a highest number right now. For example, you have this let us take this example 10. Then let me take another example. Let's say 1000 is the highest number in my sequence. 2 and mm, uh, let it, let me have the 7. Okay, and I am a and I am going to pick it. Okay, so if I start if I pick greedily 10 value, then 1000 will be available for B. Then no matter whatever I pick uh, after this, no matter if even if we are able to get any other number from from 2 or 7, we will be losing. But if instead of greedily we choose optimally, we go for 7. So in next turn, we will have to either pick 10 or 2. No matter, let it pick the 10. Then this 1000 will be available for you. So herein, basically choosing 7 over 10 is providing you the optimal solution, even if uh, 7 is smaller than 10. Okay, so greedy won't work. So what happens if we have multiple choices and uh, and we have multiple choices and we can't decide whatever which approach to choose. We basically iterate all choices, and iterating all of choices by recursion. And since number of choices can be heavy, can be large, that depends on the problem constraints, but usually those are large. So instead of iterating, uh, recalculating every state, go we go and store that, and that converts our recursion to DP. So this is a DP problem. So how do we approach this then? Okay, correct. And what are the key elements for the DP? For DP, we know that there are two things that are utmost important. One is the state. What state are we going to maintain? Other thing is the transition. How are we going to transit between from one state to other state? And the last one is the base case. Every DP problem always uh, eventually consolidate into these three principles. Okay, correct. So basically, what let us try to identify these values for our problem. What can be state for our problem? Tell me. Hmm. So given an array of size L and R, okay, we have two choices. If we pick the L, correct, then how much gain we will be getting? We will be getting value of Lth element minus whatever whoever I mean whatever the maximum value we can get. What we call this? Let me call this. See, current you will get for sure this value, and since you have taken your chance, A has taken your chance, now B will take chance, right? And whatever B will B will get out of this L plus 1 R R size, this remaining array, you will be losing that, right? You will be losing that. So eventual gain for you out of this will be this thing, right? That I'm trying to write here, that we will be getting value of L minus, let me go to this DP state, whatever the value we will get from R. So this value is being contributed by A, this value is contributed by the B, and this is our final profit that uh, we will be getting, correct? Similarly, uh, for for if we pick the rth value, we will be getting v of r minus uh, then r will be consumed, uh, and b will have the chance to pick the values from l to r minus 1, right? And whatever the value, this will be contributed by a, this will be contributed by the b, and this will be my net profit, isn't it? Correct. So kind of, is there any choice left? No. So given an array, we do have two choices. We either pick the L, the left element, we pick the right element, and we have the uh, kind of values, profit that we can get after picking each side values. And so For given range L comma R, what will be the maximum profit that we can get? Maximum will be of these two states that we have calculated above. Correct? Isn't it? Isn't it? If I write it more formally, dp of L comma R will be max of um, value of L minus dp of L plus 1 comma R, then value of R minus dp of L comma R minus 1, isn't it? So this is the state we are talking about. And see, we have already covered our transitions as well. So, okay, actually we haven't. These are just the states. Okay. Now, moving on to the transitions phase, how are we going to transit? Okay. Basically, we have to move from one state to another state. So, uh, if we know the answer of this smaller array, R comma R, uh, then can we can we answer L R minus 1? Yeah, that is true. And can we answer in the same manner L plus 1 comma R? Correct. So basically this L comma R is the superset, and these are the smaller interval in this, and we can answer this. Correct. So it it kind of looks intuitive that if we go from outer outer loop to the inner constraints and eventually try to reduce our array to the single element, and whenever the single element is comes, we will decide in our base case that which element to pick. But transition is always looking uh, towards decreasing the interval size. And how much reduction is happening in each iteration? That is by 1. That is by 1. Sorry, minus 1. That will be minus 1. So our interval size is decreasing by minus 1. Right. So transition is looks straightforward. We will try to, since we can't get to know the larger set value first, so we will start from the smaller set, smaller interval value, that will be 1, correct? At minimum, we can have a single element. This 10 is given, and A will always start. Who will be the winner? Tell me. Then A will, of course, pick the 10, and B won't be getting the chance. Although this won't be the case, because constraint is given that the size of these elements will be always either to 10, and there must be some max value, and then uh, B can pick. So it will be max of 10 comma x. But but in general, if even if single element is present, then A can pick only that element. Correct. So our interval will start from 1 to the size of uh, array, right? Right. Or for this case, we can also make it from 2 to n. Correct. Now, coming to the base case, what will be the base case? If the single element is given, just simply assign that value to A. That will be profit made by A, that initial value. If two elements are given, then A will be, the profit of A will be maximum of, again, the max value minus min value, isn't it? That will be the profit. And how do we get to know that A is the winner? I will prove at the end also that how are we driving this winner. Actually, we can do that right away. So let's see. A get X score, we get Y score, and we know that the sum of stones is the S. Then we are saying that X plus Y is S, correct? And let's see, A's profit after all of our calculation is P. Then we also know that X minus Y is equal to P, correct? Now to solve this, we simply add these two equations, and we come to know that uh, x that 2x is s plus p, correct? So x will be s plus p, right, by 2, right? That implies y will be x minus p, correct? And x value, substituting the value of x, we will be getting nothing but s minus p by 2. That will be y value, right? Now, when is condition is winning condition is that x minus uh, that the x should be greater than y, right? That is the ask. So A's contributed score should be greater than y's value. Substitute these values. S plus p by 2 is greater than s minus p by 2. 2 so 2 got cancelled. Then basically, and S also got cancelled, and we see that 2p has to be greater than 0, which implies p has to be greater than 0, greater than or equal to 0. What does it convey? It conveys that the profit of A should be always greater than equal to 0. So that will be our kind of deciding condition that we can rely on at the end of our code. Okay. So basically, we got to know, right? Now, uh, to solve this, uh, now let us go actually solve this. I will be solving by tabulation, and yeah, let me share. Okay, so let us start then. So as we discussed, we will be needing to we will need to store the DP states. So we will be using vector of vector type int DP, and what can be the file size. It is 500, so we can basically hard code it. That is up to you, up to us. If this size has been more than 10 raised to power 4 or 10 raised to power 5, then we can basically use it. But 500 is not that much, so I will kind of make it static and always use 5000 as my base limit, even if the size is less. Memory constraint won't be much issue over here, because that's why. Yeah. Okay, so that will be my TP. We will also need to pre-compute for every element, for every individual element. What if only single element is chosen? One second, let me also define the file size, and one, then basically dp of I comma I means if we are given a single element, then the value will be always that element, right? That's what we are doing over here. Now, the important thing is, as we discussed, our interval. So let me define my interval from 1 to interval less than equal to n, because interval eventually we have to cover our whole array size, right? Now let me now now once we have decided the interval, we will kind of iterate our array uh, from starting and and ending will be from that starting index to that interval. Ending will be from starting index plus interval if that is within constraint of my array size. Let me show you if that is not clear. So that will be my starting index for the array, right? Now, now for every starting index, we will first need to check that interval is less than n or not. If it is within the boundary, then we need to calculate the value. And how do we calculate the value? We so for this given range I to I plus this interval value, what will be the value? Maximum of piles of I minus dp of, if I is taken, then we will need to look for the next range, right? So this is the next range, or the piles of, if we pick the last value minus dp of, then we have to look in the left side, right? So that I'm doing, we are doing this, and eventually if we have the value, then we have to just simply check if dp of my 0 to what was the last value minus is greater than equal to 0. That's that is basically checking profit is greater than 0 or not. Okay, let us give it a try whether if it runs or not. Yeah, looks fine to me. Let me submit this. Okay, we got address sanitizer issue. Okay. What does that means? We are going some out of memory issue. 1 second. Okay. Yeah, my bad. This should be the last index, right? Isn't it? Because this is zero base indexing, right? We know that. Let me submit this. Yeah, we got it. So yeah, so that's what that is done. What will be time complexity? Let us discuss the time complexity. So basically, we are traversing once, yeah, to start the finish starting value, and then we are kind of going from the interval size and kind of hopping in our mm, original array in the hops of intervals, but we are kind of doing this this interval length will be n times, correct? And for each one of these we are hopping in the case of interval is 1, we are kind of traversing every index once, so that will be n, no doubt. So eventually this reduces to O of n square only, but since I will show you the constraint are 500, so this is well within the bounds, correct? But if we would have gone with the recursive approach, then that could be to raised to power 500, because for every element we need to uh, look uh, the every possible path. Now space complexity, uh, we are clearly O of n squared, because we are using 2D index of sizing. Yeah, so that's it for today. Please uh, let me know your feedback. Uh, yeah, thank you.